We've been talking about calculating delta H. We can do this by experiment using calorimetry, or we can infer, basically estimate, delta H through Hess's law by combining other chemical reactions where we know delta H. We can also find this from what are called standard enthalpies of formation. So delta H is the change in enthalpy, and because we're only looking at the change, we can define zero to be something that's convenient. So you think about elevation. Well, what's zero elevation? Sea level. Why is that zero? Because we all agreed to call that zero, right? Technically, I suppose the center of the earth would be zero elevation, but that's not very practical, right? So for enthalpy, we're going to define zero as the enthalpies of pure elements in their standard states. And that's just done because it's convenient. So then we have to understand, well, what is the standard state for an element? Pure element, that's not so hard. But what is a standard state? Well, for a gas, that's defined as the pure gas at 1 atmosphere of pressure. For a liquid, it's going to be whatever is or a solid, whatever is the most stable form. Some things have more than one form, like carbon. At 1 atmosphere of pressure exactly, and the temperature of interest, that's usually 25 degrees C, which is considered room temperature. In fact, it just switched. It just said it was 25 degrees outside, but now it's 28. For a substance in solution, we're looking at something with a concentration of 1 molar. So those are the definitions. The standard enthalpy change, we add this degree symbol after the delta H. And so standard enthalpy change talks about when all the reactants and the products are in their standard states, which actually is not a common occurrence, but it's the starting point. Standard enthalpy of formation is the enthalpy change when 1 mole of a pure compound is formed from its constituent elements. It's also called the standard heat of formation instead of standard enthalpy of formation. And key points here, the elements have to be in their standard states. Elements in their standard states have heats of formation of 0 because we decided it was going to be that way. And so we're going to measure enthalpy changes relative to those elements in their standard states, just like we measure altitude relative to sea level. So this is table 7.5 from your textbook, which shows standard heats of formation for a bunch of different things. This is just a few selected substances. In the appendix of your book, there is a much larger table that has a lot more stuff in it, and even that is just a small piece of all of the heats of formation that are known. And if you're interested, I'll show you the pages and pages and pages of these values in the CRC. So if we're looking up standard heats of formation, and we'll see that some of these are elements, like here's carbon. Well, carbon can exist as graphite or as diamond, so which is the standard state? Well, the standard state is the one that has the heat of formation of 0. So sometimes you're not sure which is which, or like, you've got fluorine, well, is it F or F2? Well, this will tell you it's the F2, okay? And then, if you need to look up the heat of formation, say, of methane, you can look that up right here. So speaking of methane, this is the standard enthalpy of formation or heat of formation for methane. We looked it up in the table. And this represents this chemical reaction where we're making 1 mole of methane from the elements in their standard states. So carbon as graphite and hydrogen gas. Now this does not mean that this is how you make methane, right? This is more of a theoretical thing. But this would be the formation reaction. So it's the chemical equation that describes forming 1 mole of compound from elements in their standard states. Again, if you're not sure which is the standard state, you can find the form that has the heat of formation of 0. The definition requires that we have 1 mole of product. And so to balance the chemical equation, we sometimes end up with fractions on the reactants. And the heats of formation here are kilojoules per mole because it's always set up for 1 mole. So let's look at how to write these formation reactions. Writing the formation reaction for carbon monoxide, CO gas. So we have 1 mole of product, and then we look at, well, what elements are in that compound? Well, there's carbon and there's oxygen. We're going to split it into elements. This is not separating into ions. This is just separating into its elements. The elements have to be in their standard states. We need to find the standard state for carbon. Well, that is the graphite. We know because of the heat of formation being 0. And then for oxygen, we can look it up in the table, but we also have the knowledge for a lot of these to just write down the standard states. So oxygen is one of the diatomic elements. So its standard state is O2, and it's a gas because its symbol is red on the periodic table. Okay. So here we have the correct reactants and product, but this isn't balanced. So we need to balance it, but we have to keep this, we have to keep this with a coefficient of 1. Normally we'd say, well, there's 2 oxygens, cover up that half. There's 2 oxygens, I need to put a 2 here and a 2 there. Well, we can't do that. This has to stay a 1. So 1 carbon, we need 1 oxygen, so that's 1/2 of O2. And of course that doesn't make sense on a molecular level, but if you're talking about moles of oxygen, you can have 1/2 a mole of oxygen. That's not a problem. And then you can look up the heat of formation in the table. So let's practice writing heats formation reactions. So we're going to do sodium chloride and lead 2 nitrate. So we start out by writing the product. So we're writing the equation for the formation of 1 mole of sodium chloride. And then we identify the 2 elements that are present. There's sodium and there's chlorine. So sodium's a metal, right? So we look at it on the periodic table, and what is its physical state at room temperature? It's a solid. And for the metals, we don't need to worry about them being diatomic or anything like that. So that's just the standard state of sodium. For chlorine, let's remember what we just talked about with oxygen. It's a gas, and it's diatomic, so it's Cl2. So you can go look those things up, but most of them you can just do from basic chemistry knowledge. Graphite and carbon, that's in diamond, that's a little bit different, right? There's sulfur and phosphorus are also kind of weird, but I won't try to trick you with those. So how do we balance this? We need 1/2 on the chlorine, so that we can have one chlorine on each side, 1 sodium on each side. Okay? And then it says include the values of the heat of formation. So let's go back and look up the heat of formation for sodium chloride. You see it's right over here. So it's negative 411.2. So standard heat of formation, negative 411.2 kilojoules per mole. Let's do the next one. So here we're making Pb NO3 2 solid. What elements are present in that compound? Lead Nitrate is not an element.
Oh, we need to break it up.
Yeah. So before I was like really on you, it's like there's two ions, right? It's lead 2 and nitrate ion. And that's actually a lot more important than what we're doing right now. But what we're doing now is we are breaking it into its individual elements, which students are always wanting to do, and I say you can't. So this is the one place you can, right? So we're just looking at all the capital letters, basically. There's 3 capital letters, so we have 3 elements. And then we have to identify standard states for these things. So what would lead be? A solid, because it's a metal. How about nitrogen?
Gas.
A gas. Is it diatomic? Yes, it is. So that should be N2. I didn't leave much room over here. How about oxygen?
Gas.
Also a gas, and also diatomic. So we got our elements and their standard states, and then we balance. 1 lead and 1 lead. How many nitrogens in this? 2. Because we've got the NO3, and there's 2 of them. So the N2 is fine. How many oxygens? 6. So we need to put a 3 in front of O2 to get 6. So lead nitrate is not on, it's not in table 7.5, so I pulled these out of the appendix. And so here we see the lead nitrate solid, and it's minus 451.9. So that's the heat of formation for lead nitrate. Any questions? Okay. So like I said, these are excerpts from an appendix in the back of the book. And what we're interested in right now is this heat of formation. That's the first column of numbers. The second column is delta G, which is Gibbs free energy, and the third one is entropy, and those are Chem 1b things. So we'll just be looking at the first column. So if delta H corresponds to the formation of a compound from its elements, then what if we take that compound and we break it into its elements? What's the energy change? The opposite, right? So the negative of delta H corresponds to the decomposition of the compound into its elements. So what this means is we can use these heats of formation to calculate the enthalpy change of any chemical reaction by taking the reactants and imagining we're taking them apart into their individual elements. We can look up delta H for that, and we know it's opposite, the sign. And then taking those elements and putting them together into the products, and we can look up the heats of formation from those. And then we total it all up, and that's going to give us the standard heat of reaction. We can also think of this as you can take any chemical reaction and write it as the sum of formation reactions. Remember we did Hess's law where we took like in the example, 3 chemical equations, and we switched them around and multiplied them and stuff until they added up to what we wanted. You can do that here as well. But I think it's much simpler to think of it this way, even though that looks kind of complicated. So what is this here? The standard heat of reaction is equal to the sum of the heats of formation for the products, and here the N represents the coefficient. If you're making 2 moles of product, it's going to be twice as big energy change, right? So we take the delta H for each of these things and we multiply by how many moles of it are in the equation. So those are the things that are getting formed. And then we're going to subtract, because decomposing it is opposite in sign. So we're going to add up all the heats of formation for the reactants, and we're going to subtract those from the products. And so, remember, delta is always final minus initial. So here what we're talking about is products, that's the final part of a chemical reaction, minus reactants, which is the initial part, right? So it's just final minus initial again. That's what delta means. So let's look at this. So we can draw an energy diagram representing this chemical equation. It's the combustion of methane, forming CO2 and water. So here we have the reactants. They have an enthalpy. And what we're looking at is we want to find the enthalpy change when these form CO2 and water. Well, if we don't want to measure that, we can use heats of formation to calculate that. So oxygen here is already an element in its standard state. But we're going to imagine taking the methane apart. So decomposing it. See, these are the reactions down here, the formation reactions. Carbon and 2 hydrogens make CH4. The heat of formation is negative 74.6. That's if we form a mole of it. If we decompose a mole of it, then it's plus 74.6. So now we have all elements in their standard states, and from those we're going to form CO2. So that's this guy right here, forming CO2, negative 393.5. And we're going to form 2 moles of water. So this is for water, so we need to multiply that by 2, and that's your negative 483.6. And so we add these together then, and we get this right here. So that's more of the visual method. I'm going to do that equation thing. So the standard heat of reaction here is the products, right? So we've got delta H for CO2 and 2 times delta H for H2O. And then, I've run out of screen. So what I'm going to do is I'm continuing. This is text wrapping, right? I'm text wrapping, and so it's going to wrap around down here. And so we're going to subtract the heats of formation of the reactants. Here, we changed the sign and thought about decomposing it. What we're doing here, which involves less thinking, is we're subtracting it, so that takes care of the sign change. So we're subtracting all of the reactant delta H's. So the one for methane and the one for oxygen. But what's the heat of formation for O2 gas? It's 0 because that's an element in its standard state. So this is just 0. So we're going to take the products. Here's the CO2. So that's negative 293. Sorry, negative 393.5 kilojoules per mole. And technically what we're doing here is we're saying we have 1 mole of that. And so then the moles cancel out. And then we've got 2 moles of water, and the heat of formation for water is negative 241.8 kilojoules per mole. And the moles cancel out. So those are my products, and then I'm subtracting, text wrapping again, the heat of formation of the reactant. There's 1 mole of that, and it's negative 74.6 kilojoules per mole. Again, the moles cancel out. So this is our products. So negative 393.5 plus 2 times negative 241.8 minus negative 74.6. And what do you know? We get the same number, negative 802.5 kilojoules. So that's the standard heat of formation, the standard heat of reaction for this chemical reaction. Any questions? The thermite reaction, in which powdered aluminum reacts with iron oxide, is highly exothermic and really, really fun to watch and kind of dangerous. But that's the chemical reaction. Use standard enthalpies of formation to find the heat of reaction for the thermite reaction. So what we're going to need here is we're going to need the heat of formation of Al2O3. Do we need to look up the heat of formation of iron? No, it's an element in its standard state, it's 0. And what about aluminum? Also 0. But Fe2O3 solid, we need that heat of formation also. So we're going to go back here. And up here under iron, we find Fe2O3 negative 824.2. And then aluminum is up here, Al2O3 minus 1675.7. I'm just going to write those down because I don't trust my short-term memory. So to calculate this, we're looking at the products minus the reactants. So the standard heat of formation for the products, Al2O3, and we can ignore the iron because it's 0. And then we're going to subtract the reactants. Again, the element here is 0, but we need the heat of formation for the iron. So we looked those up. So aluminum, negative 1675.7 kilojoules. And then we're subtracting negative 824.2 kilojoules per mole. Well, really what we're doing here is we're multiplying by 1 mole, right? There's 1 mole of this and 1 mole of that. And, on your calculator, let your calculator deal with the negative signs. Don't try to do some of it in your head. Just let your calculator do it. Just type it in exactly the way it says. Use that negative, not the minus sign, the negative sign, negative 1675.7 minus negative 824.2, and your calculator knows how to do that. Negative 851.5 kilojoules. So that's the standard heat of reaction for this guy. Any questions? The hardest part about this is remembering that you can do it, right? Just remembering that it's a thing. Because, on the final exam, it might say something like this. Here's this reaction. Calculate the heat of reaction. And they'll give you some heats of formation, and you're like, what? Final minus initial. Here's another one. Back to the chemical hand warmers. They produce heat when removed from their airtight wrappers. The reaction is iron plus oxygen making Fe2O3. calculate the heat of reaction for this, and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So if we look at this, and we're looking for the standard heat of reaction, heat's the formation of the product minus the reactants. Both of the reactants are elements. So this one's pretty nice. The standard heat of reaction here is 2 moles times the heat of reaction for Fe2O3. Well, nicely, we already have that one written on the board because we used it in the previous example. So we have negative 824.2 times 2. That's a really sad delta. We can do better than that. So negative 1648.4 kilojoules. It is close to Al2O3, isn't it? Okay, so that was the first question. Calculate delta H. There's a number given here. 15 grams of iron powder. So this is one of those thermostoichiometry problems where we have a mass of one of these things and we have energy involved. So we should think stoichiometry, grams to moles to moles to grams, right? So they gave us grams of iron, so we'll go grams of iron to moles of iron, and then we're trying to get to energy. Do we need to go to moles of something else? No, we can go straight to kilojoules. Because this number relates directly to each of these. This is the amount of kilojoules for 4 moles of iron. So that's our path. 15.0 grams of iron. We're going to convert to moles of iron and then to kilojoules. So we're dividing by grams of iron, so those units cancel out. Dividing by moles of iron, so those units cancel out. Moles and grams, molar mass, periodic table, 55.85. And then this one, this is from the chemical equation. So delta H is negative 1648.4 for how many moles of iron? For 4 moles of iron. 15 divided by 55.85 times negative 1648.4. And then the thing I often forget, divided by 4. I actually forgot it in lecture yesterday, and thankfully somebody said, hey. Starting number has 3 sig figs, so our results should have 3 sig figs. Now, if this was a practice exam question or on mastering chemistry, and you put in negative 111 kilojoules, it'd say, wrong. It's plus 111 kilojoules. It's because we have words telling us the direction. How much heat is produced? If I ask you how much you paid for that pair of shoes, are you going to say, I paid negative $100? No, we understand that you spent the money. You don't have to tell me it's negative, right? So that's what we're doing here. It produced 111 kilojoules. Now, if we want to just say Q, what's Q? the amount of energy associated with this process, where it doesn't specify direction, then we need the negative sign. So that can be kind of confusing. I won't try to trick you with that one. Any questions? Yeah, and there the answer is positive.